The moon is a death trap, and we're about to walk right into it. Forget the romantic images of lunar bases and Earth rising over silver horizons. The reality: microscopic assassins lurking in the dust. Radiation that shreds your DNA. An environment so hostile it makes the Sahara look like a beach resort. We're planning humanity's next home on a surface designed to kill us. Speaking of things you should actually see with your own eyes, grab my ebook Mars in 15 minutes right now. It's the fastest way to go from walking past Mars every night to actually recognizing it from Earth instantly. Just 15 minutes of reading, and you'll know exactly where to look and what you're seeing tonight. Links in the description and pinned in the comments. Now let's begin. We stand at the edge of a new era. The Artemis program isn't just about planting flags and taking photographs like Apollo did back in 1969 through 1972. This time, we're going back to stay. NASA has committed $20 billion to building a permanent lunar base near the South Pole. China and Russia have announced their own plans for a joint research station. Private companies like SpaceX and Blue Origin are designing cargo landers that could deliver tons of equipment to the surface. The timeline? Astronauts could be living on the moon within the next 10 to 15 years. This isn't science fiction anymore. The rockets exist. The technology is real. The international agreements are being written as we speak. We are genuinely preparing to become a two-world species. But as we get closer to making this dream a reality, scientists studying the lunar environment have discovered something deeply troubling, something that makes the challenges of getting to the moon look almost trivial compared to the challenges of actually surviving there for months or years at a time. You see, when the Apollo astronauts returned from their brief visits to the lunar surface, they brought back more than just rock samples and incredible stories. They brought back warnings. Warnings that we're only now beginning to fully understand. Eugene Cernan, commander of Apollo 17, described moon dust as one of the most significant environmental concerns they faced. Harrison Schmitt, the only geologist to walk on the moon, experienced something alarming. After just a few hours of exposure to lunar dust inside the cabin, he had a severe allergic reaction. His sinuses became inflamed. He struggled to breathe properly. These weren't minor inconveniences. These were genuine medical emergencies waiting to happen, and they occurred after less than 3 days on the surface. Now imagine what could happen during a 6-month stay, or a year, or a permanent posting. The problem is this: lunar dust isn't like anything we have on Earth. It's been created through billions of years of micrometeorite bombardment, smashing volcanic rocks and glass into an ultrafine powder. Without wind or water to wear down the edges, every single particle is razor sharp. Under an electron microscope, moon dust looks like broken glass mixed with tiny daggers, and because the moon has no atmosphere to shield it from radiation, this dust has been electrically charged by the solar wind for eons. This means it sticks to everything: spacesuits, equipment, tools, boots, hair, skin. The Apollo astronauts couldn't brush it off. They couldn't shake it free. It clung to their gear with an almost supernatural persistence, carried into their lunar modules on their suits, and immediately began causing problems. But it gets worse, much worse. In 2024, NASA released an updated risk assessment document called The Risk of Adverse Health Effects Due to Celestial Dust Exposure. This wasn't some speculative paper about theoretical dangers. This was based on decades of research analyzing actual Apollo-era dust samples, combined with new laboratory studies that simulated lunar surface conditions. And what they found should concern anyone excited about lunar colonization. When lunar dust particles are inhaled, they don't behave like terrestrial dust. Because they're so sharp and so small, they can penetrate deep into lung tissue, potentially causing inflammation and scarring. Studies conducted on human lung cells exposed to simulated lunar dust showed significant toxicity. The dust particles damaged cell membranes, triggered inflammatory responses, and in some cases caused cell death. Before you download my ebook, Mars in 15 Minutes, let me tell you why this matters for the bigger picture of space exploration. Understanding the Moon's challenges isn't just about lunar colonization. It's about learning how to survive on any airless world in our solar system. Mars has its own dust problems. Asteroids we might mine are covered in regolith with similar properties. If we can't solve the dust problem on the Moon, which is only 3 days away, how will we ever establish ourselves on worlds that take months to reach? My free guide helps you start your own cosmic journey by observing our neighboring planet from your backyard. But it's this kind of big picture thinking that makes space exploration so interconnected. Every challenge we face on the Moon teaches us something vital about our future among the stars. Grab your copy in the description below, and let's continue exploring why these dusty grains matter so much. But the respiratory hazards are just the beginning. The dust is also abrasive enough to damage equipment. During the Apollo missions, the fine particles work their way into mechanical joints, scratched helmet visors, degraded seals, and contaminated life support systems. One astronaut reported that his spacesuit's joints became noticeably stiffer after just a single moonwalk. Another found that the dust had abraded through multiple layers of his boot material. These weren't long-duration missions. These were visits lasting only 72 hours at most. The astronauts did a handful of moonwalks, spent limited time outside, and then came home. Even in that incredibly short window, the dust proved to be a relentless adversary. Now scale that up. Imagine a crew stationed at a lunar outpost for 6 months. They'll be going outside regularly to conduct experiments, maintain equipment, collect samples, and explore the surrounding terrain. Every single time they return to the habitat, they'll bring dust with them. Airlocks can help, but they can't eliminate the problem entirely. The electrostatic charge makes the particles cling to fabric and metal with remarkable tenacity. Over weeks and months, that dust will accumulate inside living spaces. It will get into the air circulation systems. It will settle on surfaces where astronauts eat and sleep. It will become an inescapable part of daily life, and every breath they take could be pulling those microscopic glass shards deeper into their lungs. NASA knows this. They're not ignoring the problem. In fact, researchers at Johnson Space Center in Houston have dedicated entire laboratories to studying lunar dust mitigation strategies. I visited these facilities virtually through their published research, and what I found was both impressive and sobering. They've developed something called an electrodynamic dust shield. It sounds like science fiction, but it's real technology. The system uses electric fields to literally repel charged dust particles from surfaces. Imagine an invisible force field that pushes the dust away before it can stick to your spacesuit or equipment. In laboratory tests, these shields can remove up to 90% of lunar dust simulant from surfaces. 90% sounds fantastic, right? But here's the problem. That remaining 10% is still catastrophic over long periods, and the shields require power, constant power. On the Moon, where every watt of electricity is precious and has to come from solar panels or nuclear reactors, running continuous dust-repelling force fields on every surface that matters becomes a massive engineering challenge. Other teams are developing specialized fabrics and materials that resist dust adhesion. They're designing airlock systems with multiple chambers to minimize contamination. They're creating vacuum cleaning systems that can operate in the lunar environment. Some engineers are even proposing that habitats should be built underground or inside lava tubes where astronauts would have minimal exposure to surface dust. But every solution creates new problems. Underground habitats are protected from dust and radiation, but they're incredibly difficult and expensive to construct. You'd need heavy excavation equipment, or you'd have to find natural caves and lava tubes in exactly the locations where you want to build your base. Advanced airlock systems add weight, complexity, and points of potential failure. Dust-resistant materials need to be tested for years in actual lunar conditions before we can trust them with human lives. And here's something that keeps mission planners awake at night. We've never actually tested any of these solutions for longer than a few weeks in simulated conditions. The longest anyone has ever spent dealing with real lunar dust in the real lunar environment was 3 days. That's it. We're about to commit billions of dollars and human lives to missions lasting months or years, and we're essentially making educated guesses about whether our dust mitigation strategies will actually work. But as terrifying as the dust problem is, it's not even the most dangerous threat facing lunar colonists. Not by a long shot. Let me tell you about something invisible, something that silently damages human cells every single second you're on the lunar surface. Something that Earth's magnetic field and thick atmosphere protect us from so completely that most people don't even realize it exists. Radiation. Space radiation isn't like the radiation from a medical X-ray or even from a nuclear power plant accident. It's fundamentally different, and it's everywhere beyond Earth's protective bubble. There are two primary sources we need to worry about: galactic cosmic rays and solar energetic particles. Galactic cosmic rays, or GCRs, are high-energy particles that have been accelerated to nearly the speed of light by supernova explosions, black holes, and other violent cosmic events happening across the universe. These particles have been traveling through space for millions or even billions of years. Some of them have originated from stars that died before our sun was even born, and they're constantly bombarding everything in our solar system. When I say constantly, I mean every second of every day. These particles are sleeting down from space. On Earth, we barely notice them because our planet's magnetic field deflects most of them, and our atmosphere absorbs the rest. The few that do make it through are harmless at ground level. The Moon has no magnetic field. It has no atmosphere. Every single cosmic ray that happens to be passing through that region of space slams directly into the surface and anything on it. In 2020, Japanese researchers published a comprehensive study in the Journal of Radiological Protection calculating the exact radiation dose astronauts would receive on the lunar surface. The numbers are shocking. They estimated that astronauts would be exposed to approximately 416 millisieverts per year from galactic cosmic rays alone. To put that in perspective, the current career limit for NASA astronauts is 600 millisieverts total. That's the maximum radiation dose NASA considers acceptable for an astronaut's entire career in space. On the Moon, you'd receive more than 2/3 of that limit in just 1 year. But wait, it gets worse. That 416 millisievert figure assumes you're out on the open surface with minimal shielding. It also only accounts for the chronic constant exposure from galactic cosmic rays. It doesn't include the second, even more terrifying source of radiation: solar energetic particle events. The sun isn't a steady, unchanging ball of light. It's a roiling cauldron of plasma with a magnetic field that's constantly twisting, breaking, and reconnecting. Sometimes these magnetic field lines snap like overstressed rubber bands, releasing enormous amounts of energy in what we call solar flares. The most powerful flares can be accompanied by coronal mass ejections, where the sun literally hurls billions of tons of charged particles into space at millions of miles per hour. When these solar storms are aimed at Earth, we get beautiful auroras. The particles hit our magnetic field, get channeled toward the poles, and create shimmering curtains of light in the sky. It's gorgeous. It's harmless to us on the ground. On the Moon, a major solar energetic particle event is a potential death sentence. Let me tell you about August 1972. Between Apollo 16 and Apollo 17, a massive solar storm erupted. It was one of the most powerful events recorded in the space age. If astronauts had been on the moon during those few days, they would have received a radiation dose estimated at over 2,000 millisieverts. 2,000 millisieverts. In a matter of hours or days, at that level, astronauts would have experienced acute radiation syndrome, nausea, vomiting, fatigue, damage to their bone marrow and immune systems. Some might have died within weeks. Others would have faced dramatically increased cancer risks for the rest of their lives, assuming they survived the immediate effects. And here's the truly terrifying part. We can't predict these events with much accuracy. We can sometimes see the flare on the sun and know that particles are coming, which gives us maybe 8 to 24 hours of warning depending on the speed of the particles. But we can't tell you a week in advance that a major solar storm is going to happen. We can barely tell you a day in advance. Modern research published in 2026 by the German Aerospace Center calculated that you'd need more than 4 grams per square centimeter of lunar regolith, which is moon dirt, as shielding to reduce the radiation from a major solar particle event to below NASA's 30-day exposure limits. 4 grams per square centimeter might not sound like much, but when you're talking about shielding an entire habitat or rover, you're talking about tons and tons of material that has to be moved and positioned. The European Space Agency conducted a study in 2025 examining the psychological requirements for long-duration lunar missions. They identified something they called environmental monotony stress. Unlike Mars, which has weather patterns, seasonal changes, and a dynamic atmosphere that creates variety in the landscape, the Moon is static, the same grey regolith, the same black sky, the same unchanging horizon. Day after day after day, astronauts who've spent time in extreme isolation on Earth, like winter-over crews at Antarctic research stations, report that the sameness of the environment becomes psychologically wearing over time. Some develop what researchers call polar madness or winter-over syndrome, characterized by depression, irritability, insomnia, and cognitive impairment. Antarctica at least has weather, storms, wind, changing ice formations. The Moon offers none of that variation. It's a dead world, and being constantly reminded of that fact takes a psychological toll that we're only beginning to measure in analog studies here on Earth. But let's return to the physical dangers, because we've only scratched the surface. Literally, the Moon experiences temperature swings that would be lethal to unprotected humans within minutes. During the lunar day, which lasts about 14 Earth days, surface temperatures in direct sunlight can reach 127 degrees Celsius. That's 260 Fahrenheit, hot enough to boil water if water could exist as a liquid on the airless surface. Then the sun sets, and for the next 14 Earth days, temperatures plummet to minus 173 degrees Celsius. That's minus 280 Fahrenheit, cold enough to freeze carbon dioxide into dry ice. These aren't gradual transitions. The boundary between sunlight and shadow on the Moon is sharp and absolute. Step from light into shadow, and the temperature can drop by 300 degrees in an instant. This creates enormous thermal stress on equipment and spacesuits. Materials expand in the heat and contract in the cold. Seals that work perfectly at room temperature can fail when subjected to these extremes. Metal components can crack. Electronic systems can malfunction. NASA's technical briefs on lunar habitat design, published in 2026, identify thermal management as one of the most challenging engineering problems for sustained lunar presence. You need heating systems powerful enough to keep habitats warm during the 14-day night, but you also need cooling systems capable of rejecting excess heat during the 14-day day. Both systems need to function flawlessly for months or years without maintenance, and you can't just open a window to cool down or warm up. There is no air. The vacuum of space surrounds you constantly. Living in a vacuum creates hazards that most people never consider. On Earth, air pressure pushes against every surface of your body with about 14.7 pounds per square inch. You don't notice it because the pressure inside your body pushes back with equal force. Everything is balanced. In the vacuum of space, there's nothing pushing on the outside. If your spacesuit ruptures, the air inside rushes out, and you have about 15 seconds of useful consciousness before you pass out from oxygen deprivation. Your blood doesn't boil, contrary to popular science fiction, but the moisture on your tongue and in your eyes starts to evaporate immediately. You'd survive for maybe 90 seconds in total if someone could get you back into a pressurized environment quickly enough. But here's what makes this scenario truly nightmarish on the Moon. There's no immediate rescue. On the International Space Station, if an astronaut's spacesuit develops a leak during a spacewalk, they can get back inside the airlock in minutes. On the Moon, you might be kilometers away from your habitat when disaster strikes. Your rover could have a flat tire, you could fall into a crater, equipment could fail. Every single moonwalk is a carefully calculated risk. And the more time you spend outside, the more opportunities there are for something to go wrong. The Apollo program was lucky. Incredibly, almost impossibly lucky. Across 6 successful landing missions, 12 astronauts walked on the Moon for a combined total of about 80 hours. Not a single one experienced a catastrophic suit failure. Not one fell into a deep crater they couldn't climb out of. Not one was caught outside during a solar radiation event. Statistical analysis published in 2024 by mission safety experts suggests that if we're conducting regular moonwalks over months and years, eventually our luck will run out. Not because the equipment is poorly designed, but because probability catches up with you. When you're pushing the boundaries of what's possible in an environment with zero margin for error, the question isn't if an accident will happen, it's when. And this brings us to something that doesn't get discussed nearly enough in public presentations about lunar colonization: medical emergencies. What happens if an astronaut on the Moon has a heart attack, or breaks a leg during a fall, or develops appendicitis, or suffers severe radiation exposure during an unpredicted solar storm? On the International Space Station, emergency medical return to Earth can be accomplished in a matter of hours. Launch a Soyuz or Crew Dragon, undock, deorbit, and you're on the ground receiving advanced medical care within half a day. From the Moon, the journey home takes 3 days minimum. 3 days while someone is having a medical crisis in an environment where even basic procedures like surgery are monumentally difficult. How do you perform an operation in lunar gravity, which is 1/6 of Earth's? How do you manage bleeding when blood doesn't behave the way doctors are trained to expect? How do you maintain sterile conditions when lunar dust contaminates everything? NASA has teams of flight surgeons and medical experts working on these problems. They're developing telemedicine protocols where doctors on Earth can guide astronauts through procedures using virtual reality and robotic assistance. They're training astronauts in emergency medicine far beyond basic first aid. They're designing medical facilities that can function in partial gravity and vacuum conditions. But again, these are systems that have never been tested in actual lunar emergencies. We're making educated guesses about what will work when someone's life depends on us getting it right the first time. Research published in Nature in 2026 proposed a phased approach to dealing with these challenges. Start with short-duration missions, similar to Apollo, but with better technology. Gradually extend the mission length as we gain confidence in our systems. Build up infrastructure robotically before committing to permanent human presence. Establish supply depots, power systems, and emergency shelters that can support longer stays. It's a sensible, cautious approach, but it's also slow and expensive, and it conflicts with the political and economic pressures to show dramatic progress quickly. There's a fundamental tension at the heart of lunar colonization that nobody likes to talk about publicly. Space agencies and private companies announce ambitious timelines: bases by 2030, mining operations by 2035, permanent settlements by 2040. These dates sound concrete. They inspire confidence and attract funding. But the engineers and scientists working on the actual technology know something different. They know that every system needs years of testing. They know that unexpected problems always emerge. They know that the gap between a successful prototype in a laboratory on Earth and a reliable system operating on the Moon for months without maintenance is vast and expensive to bridge. I spoke with several researchers who work on lunar mission planning, and off the record, many of them expressed deep concern about the rush to establish permanent presence before we've adequately solved the fundamental problems. They worry that political pressure and commercial competition could lead to cutting corners. And on the Moon, there are no corners you can safely cut. But let's assume we overcome the radiation challenges, the dust problems, the temperature extremes, and the medical risks. Let's assume we successfully establish a small outpost with a rotating crew of astronauts living in heavily shielded habitats, venturing out in advanced spacesuits and somehow managing to stay healthy and sane for months at a time. Now comes the next terrifying question. How do you keep them alive without constantly shipping supplies from Earth? This is where the concept of in situ resource utilization, or ISRU, becomes critical. The idea is elegant. Instead of bringing everything you need from Earth at enormous cost, you manufacture what you need from local materials. You mine the Moon. You extract useful elements. You create oxygen, water, rocket fuel, and construction materials from lunar regolith. It sounds perfect in theory. In practice, it's fiendishly difficult. Let's start with water, because water is absolutely fundamental to human survival. You drink it, obviously, but you also use it for hygiene, for growing food, for radiation shielding, and critically, you can split it into hydrogen and oxygen for rocket propellant. Water is possibly the most valuable substance you could find on the Moon. The problem is, for most of the 20th century, we thought the Moon was completely dry, bone dry. Analysis of lunar samples brought back by Apollo showed no evidence of water molecules in the regolith. The Moon formed from a catastrophic collision between early Earth and a Mars-sized object, and the tremendous heat of that impact was thought to have driven off all volatile compounds, including water. Then, starting in the 1990s, things got interesting. The Clementine mission in 1994 detected hints of ice in permanently shadowed craters near the lunar poles. The Lunar Prospector mission in 1998 found more evidence. In 2009, NASA deliberately crashed the El-Koros-S spacecraft into a shadowed crater and analyzed the debris plume. They confirmed the presence of water ice. Suddenly, lunar colonization seemed far more feasible. If there's water ice at the poles, you could set up a base there, mine the ice, and solve your water problem. You could produce oxygen for breathing and hydrogen for fuel. The economics of lunar settlement completely change if you don't have to ship water from Earth. But here's where reality gets complicated. The amount of ice, its concentration, its accessibility, and its distribution remain deeply uncertain even today. In 2026, scientists from Brown University published a comprehensive review in the journal Icarus, examining all available data on lunar polar ice. Their conclusions were sobering. Yes, there's definitely water ice in permanently shadowed regions, but it's not lying around in convenient frozen lakes you can just scoop up. It's mixed into the regolith at concentrations that vary wildly from place to place. Some areas might have 5 to 10% ice by weight, others have less than 1%. To put that in perspective, imagine trying to extract enough water to support a crew of 4 astronauts who need several liters each per day for drinking, hygiene, and life support systems. You'd need to excavate, heat, and process tons and tons of regolith to extract relatively small amounts of water. This requires heavy machinery, enormous amounts of energy, and complex processing equipment. And you'd have to do all of this in permanently shadowed craters where the temperature is minus 240 degrees Celsius, among the coldest places in the entire solar system. Your equipment has to function in these extreme conditions while simultaneously heating regolith to several hundred degrees to drive off the water vapor, which you then have to capture and condense. The technical challenges are immense. But even more concerning is the question of whether there's enough ice in accessible locations to support a sustained human presence. The Brown University study estimated that the total amount of water ice at both lunar poles might be anywhere from 100 million to 1 billion tons. That sounds like a lot, but the uncertainty is enormous, a factor of 10 difference between the low and high estimates. And if the actual amount is closer to the low end of that range, and if it's distributed across hundreds of small deposits rather than concentrated in a few large ones, the economic viability of lunar ice mining becomes questionable. You might spend billions developing the extraction technology and infrastructure, only to find that it's still cheaper to ship water from Earth. NASA's Volatiles Investigating Polar Exploration Rover, or VIPR, was scheduled to launch and study these questions in detail. The mission was designed to map ice deposits, measure concentrations, and identify the best locations for future resource extraction. Unfortunately, funding challenges and mission reprioritization led to its cancellation, though efforts are being made to find alternative approaches to gather this critical data. The uncertainty about lunar ice highlights a broader problem. We're trying to plan a permanent human presence on a world we still don't fully understand. Yes, we've been there. Yes, we've brought back samples and studied them intensively, but the moon is huge, about the same surface area as Africa. We've explored tiny fractions of it. We have vast gaps in our knowledge about resource distribution, geological structure, and local environmental conditions. Beyond water, there are other resources we'd need to extract. Oxygen, for example. Lunar regolith is about 40 to 45% oxygen by weight, chemically bound in minerals like ilmenite and feldspar. If you could extract that oxygen efficiently, you'd solve your breathing problem and have oxidizer for rocket fuel. Multiple companies and research institutions are developing technologies to do exactly this. Molten regolith electrolysis, chemical reduction using hydrogen brought from Earth, carbothermal reduction using carbon monoxide. Each approach has advantages and disadvantages. Each requires significant power and infrastructure. And here's the critical point. None of these oxygen extraction technologies have been demonstrated at scale in actual lunar conditions. We have laboratory prototypes. We have simulations using lunar regolith simulants, materials designed to mimic the properties of real moon dust. But simulating lunar conditions on Earth is extraordinarily difficult. You can't perfectly replicate the vacuum. You can't replicate the radiation environment. You can't replicate 1/6 gravity for extended periods. This means that when we finally do deploy these systems on the moon, we'll be conducting the real field test. And if something doesn't work as expected, astronauts' lives could depend on troubleshooting the problem in spacesuits while dealing with all the other hazards we've already discussed. The challenge of resource extraction points to an even more fundamental problem: energy. Everything humans do on the moon will require enormous amounts of power. Heating habitats during the 14-day night, running life support systems, operating communication equipment, powering rovers and construction equipment, processing regolith to extract resources, charging spacesuits, running scientific instruments, producing propellant for return journeys or transport to lunar orbit. A small habitat supporting 4 crew members would need at least 20 to 30 kilowatts of continuous power just for basic life support and operations. That's roughly equivalent to the power consumption of 2 to 3 typical American homes running all their appliances simultaneously 24 hours a day for months on end. Now multiply that by the power needed for industrial operations like ice mining and oxygen production, and you're looking at hundreds of kilowatts or even megawatts of power generation capacity. On Earth, this wouldn't be a problem. We have power grids, backup generators, and multiple redundant systems. If one power source fails, others take over seamlessly. On the moon, you need to generate all your power locally, and a single extended power failure means death for everyone in the habitat within hours as life support systems shut down and temperatures plummet. The obvious solution is solar power. The sun shines on the moon for 14 continuous Earth days, and without an atmosphere to absorb or scatter the light, solar panels receive about 30% more energy than they would on Earth's surface. During the lunar day, solar power seems ideal, but then the sun sets, and for the next 14 days you're in total darkness. How do you keep your habitat powered through 14 days of night? You need energy storage, lots of it, and this is where the numbers become truly daunting. Battery technology has improved dramatically over the past decade, but even the best lithium-ion batteries store only about 250 watt-hours per kilogram. To store enough energy to power a small habitat through the lunar night, you'd need batteries weighing several tons. Shipping those batteries from Earth would cost millions of dollars. You could potentially manufacture batteries on the moon using local materials, but that requires even more infrastructure, more power for processing, and technologies that don't exist yet beyond the conceptual stage. Some mission planners propose using nuclear power instead. A small nuclear reactor could provide constant, reliable power regardless of day or night cycles. The technology exists. NASA developed the kilopower reactor specifically for space applications, and it successfully completed ground testing in 2018. A single kilopower unit could provide 10 kilowatts of continuous power for over 10 years. Multiple units could be deployed to meet higher power demands. Nuclear power eliminates the energy storage problem entirely and provides a reliable baseline for habitat operations. But nuclear reactors bring their own challenges. They're heavy, requiring significant launch mass. They need cooling systems that work in vacuum and extreme temperatures. They contain radioactive materials that require careful handling and shielding, and there are political and regulatory hurdles to launching nuclear materials into space, even though multiple nations have done so before. Most concerning, though, is the question of what happens if something goes wrong. A reactor malfunction on Earth can be contained and managed. A reactor malfunction on the Moon, where you have limited personnel, limited equipment, and no possibility of outside help for days, could be catastrophic. Research published in 2025 by the International Atomic Energy Agency examined safety protocols for space-based nuclear systems. Their recommendations included extensive automation, multiple redundant safety systems, and the ability to safely shut down the reactor remotely if necessary. All of this adds complexity, mass, and cost to an already expensive system. Another power option being seriously considered is placing solar panels at the lunar poles, where certain elevated areas receive near constant sunlight. These peaks of eternal light experience only brief periods of darkness, hours rather than weeks. A solar array positioned on one of these peaks could provide nearly continuous power. This sounds perfect, but reality intrudes once again. The peaks of eternal light are small, elevated areas surrounded by deep, permanently shadowed craters. Building infrastructure on these peaks means working on steep, uneven terrain. You need long power cables running down into the craters where the ice deposits are located. Those cables have to withstand the temperature extremes and radiation exposure without degrading, and you're still not getting truly continuous power. Even the best peak locations experience about 10 to 15% darkness over a lunar year. You still need energy storage or backup power systems. A comprehensive study by the Lunar Exploration Analysis Group in 2026 concluded that realistically, lunar bases will need hybrid power systems combining solar, nuclear, and energy storage. This provides redundancy, which is absolutely critical for life support. If one system fails, others can keep the habitat running while repairs are made. But hybrid systems mean more mass, more complexity, more points of failure, and more maintenance requirements. And someone has to maintain all of this equipment in spacesuits, in vacuum, exposed to radiation and dust, at temperature extremes that can crack metal and degrade lubricants. Every single component needs to be designed for reliability far beyond what we accept on Earth. On Earth, if your car breaks down, it's an inconvenience. If a critical system breaks down on the Moon, people die. This means extensive testing, multiple redundancies, and careful procedures for everything. It means missions take longer and cost more than initial optimistic estimates. Let me give you a concrete example of how these seemingly minor technical challenges cascade into major problems. Consider something as simple as a bolt. On Earth, you fasten two pieces of equipment together with a standard bolt and nut. The threads engage, you tighten it with a wrench and it holds. Simple, reliable. We've been doing it for centuries. On the Moon, that same bolt faces challenges that can cause it to fail in ways you'd never experience on Earth. The temperature cycles cause the metal to expand and contract repeatedly. Without air or moisture, there's no oxidation layer forming on the surface, which means metal surfaces can cold weld together at the molecular level. The vacuum of space causes some lubricants to evaporate or decompose. Lunar dust infiltrates the threads, acting like an abrasive that grinds away at the metal with every temperature cycle. Engineers at the European Space Agency published a detailed analysis in 2025 documenting how a standard steel bolt failed after just 50 temperature cycles in simulated lunar conditions. The threads had worn down to the point where the bolt could no longer maintain proper torque. In a critical application, this could lead to structural failure, loss of pressure seal, or equipment malfunction. The solution is to design specialized fasteners using exotic materials and coatings that can withstand lunar conditions. But now your simple bolt costs hundreds or thousands of dollars instead of a few cents. And you need these specialized components for every single mechanical connection in every piece of equipment on the entire base. Multiply this across thousands of components: seals, bearings, hinges, connectors, valves, motors, pumps, and you begin to understand why lunar hardware is so expensive and why development takes so long. Every single part needs to be reimagined for an environment that's actively hostile to human technology. And despite all this careful engineering, things will still break. Equipment will malfunction. Unexpected failures will occur. This is inevitable when operating complex systems at the edge of what's technologically possible. The question is, what happens when something critical fails? Let's look at some historical examples from space exploration to understand the razor-thin margins we're dealing with. Apollo 13 is the most famous near disaster in space history. An oxygen tank exploded in the service module, crippling the spacecraft on its way to the Moon. The crew was 200,000 miles from Earth when it happened. Through extraordinary ingenuity, teamwork, and yes, a significant amount of luck, they made it home safely. But here's the crucial point: they were able to abort the mission and return to Earth. The Lunar module, designed to land 2 people on the Moon, became a lifeboat for 3 people on the journey home. It was uncomfortable, cold, and terrifying, but it was possible because they could always point the spacecraft toward Earth and use whatever resources remained to get there. If Apollo 13 had happened after they'd landed on the Moon, the outcome would have been very different. The lunar module would already be on the surface. The command module would be orbiting overhead with no way to land and rescue them. They'd be stranded on the Moon with limited consumables and no way home. Modern mission planning accounts for these scenarios. Current concepts for lunar bases include emergency shelters, redundant life support systems, and abort-to-orbit capabilities where crew can launch from the surface on short notice if necessary. But every one of these safety measures adds mass, complexity, and cost to the mission, and some emergencies simply can't be mitigated no matter how much you prepare. In 1971, the crew of Soyuz 11 became the only humans to die in space itself, as opposed to during launch or re-entry. A valve malfunctioned during the return to Earth, causing their spacecraft to depressurize. All 3 cosmonauts were dead within about 40 seconds. The spacecraft successfully landed on autopilot, but when the recovery team opened the hatch, they found the crew had already been gone for hours. A single point of failure, a valve that opened when it shouldn't have, killed everyone aboard. And this was in a spacecraft that had been tested extensively, flown multiple times, and represented the best Soviet engineering of the era. On the Moon, there are thousands of such potential single points of failure: a seal on your spacesuit helmet, a pressure valve in your habitat, a power regulator in your life support system, an airlock door that fails to close properly, a computer that glitches at the wrong moment. The terrifying reality is that no amount of testing can identify every possible failure mode. Engineers do their best with failure mode and effects analysis, examining each component and asking what happens if it breaks. They design redundancies and backups, they test and retest, but complex systems interact in unexpected ways, and sometimes failures cascade in ways nobody anticipated. In 2003, the Space Shuttle Columbia disintegrated during re-entry because of damage caused by a piece of foam insulation that struck the wing during launch. Foam shedding had happened on previous launches without catastrophic results. Engineers knew about it but had normalized the risk. They didn't fully understand how the foam strike compromised the thermal protection system until it was too late. 7 astronauts died because of a piece of foam. The investigation revealed systemic problems in how NASA assessed and communicated risk. The same organizational and psychological factors that contributed to Columbia also contributed to the Challenger disaster 17 years earlier. Different technical causes, same underlying issues: pressure to maintain schedule, normalization of deviance, and inadequate communication of risk. These aren't just NASA problems, they're human problems. They emerge in any complex organization dealing with high-stakes operations under budget and schedule pressure. And they will emerge in lunar colonization efforts as well, whether conducted by government agencies or private companies. Research in system safety engineering, published in journals like Safety Science and Reliability Engineering and System Safety, shows that accidents in complex technical systems are rarely caused by a single component failure. They result from interactions between technical, human, and organizational factors that align in unexpected ways. On Earth, we've built up institutional knowledge through hard-won experience. We've had accidents investigated them thoroughly, and implemented changes to prevent similar failures. The aviation industry is extraordinarily safe today precisely because it learned from decades of accidents and near misses. For lunar operations, we don't have that accumulated experience base. We can simulate and plan and test, but we won't truly know what we don't know until we're actually doing it, and the learning curve will be paid in blood unless we proceed with extraordinary caution. This brings us to another uncomfortable truth. Rescue and emergency response on the Moon range from extremely difficult to impossible. On Earth, if you're in trouble, help can potentially reach you quickly. Emergency services, Coast Guard, search and rescue. Even in remote locations like Antarctica or the middle of the ocean, rescue operations can be mounted within hours or days. From the Moon, rescue is essentially impossible on any timescale that would matter for most emergencies. If your habitat depressurizes, you have minutes, not hours. If your life support fails, you have hours, not days. If you're injured during a moonwalk far from base, you might have minutes to an hour, depending on the nature of the injury and your suit's remaining consumables. There's no ambulance coming. There's no helicopter extraction. The nearest help is on Earth 3 days away, and they can't do anything except watch and provide advice over a time-delayed radio link. This isolation fundamentally changes how you have to think about mission planning. Every crew member needs extensive medical training because they are the only medical help available. Every possible medical emergency needs supplies and equipment pre-positioned on the base. And for certain emergencies, severe trauma, internal bleeding, conditions requiring surgery beyond basic procedures, there simply may be no effective treatment option available. A study published in 2024 in the journal NPJ Microgravity examined medical capabilities needed for long-duration lunar missions. The authors concluded that supporting a crew of 6 for 6 months would require medical equipment and supplies massing at least 500 kilograms, plus at least 2 crew members with advanced medical training equivalent to physician assistants or paramedics. And even with all that preparation, the study identified multiple scenarios where the crew would be unable to provide adequate care: appendicitis requiring emergency surgery, severe burns from a fire, compound fractures, certain cardiac emergencies, internal injuries from accidents. In many of these cases, the only option would be immediate evacuation to Earth, a process that takes a minimum of 3 to 4 days, even if a return vehicle is ready to launch immediately. 3 to 4 days is a lifetime when someone is dying. Some mission architectures propose keeping a spacecraft constantly ready for emergency return, fueled and prepped on the pad. But maintaining this readiness consumes resources, requires personnel dedicated to spacecraft maintenance, and still doesn't solve the problem for injuries or conditions where 3 days is too long. The brutal calculus of lunar colonization includes accepting that some emergencies will be fatal regardless of preparation. This isn't speculation or pessimism, it's simple physics and logistics. And anyone volunteering for long-duration lunar missions needs to understand and accept this risk. Which brings us to perhaps the most fundamental question underlying all of this technical discussion. Why? Why are we doing this? What's the actual rationale for establishing a permanent human presence on the Moon? The answers you get depend on who you ask, and frankly, many of them don't withstand serious scrutiny. Let's start with the most commonly cited justification: science. Yes, there's valuable science to be done on the Moon. The far side offers a radio-quiet environment ideal for certain astronomical observations. Lunar geology can teach us about the early solar system. Permanently shadowed craters preserve volatiles that can tell us about the delivery of water to the inner solar system. The Moon provides a natural laboratory for studying planetary processes, all true, all interesting, But do these scientific goals require permanent human presence? Robotic missions can accomplish most lunar science objectives at a tiny fraction of the cost and risk of human missions. The rovers and landers we've sent to Mars have revolutionized our understanding of that planet without putting any humans at risk. The James Webb Space Telescope is returning astronomical data far beyond what any lunar telescope could provide, and it didn't require building a habitat at the lunar South Pole. When pressed, advocates for human lunar presence argue that humans are more flexible and capable than robots. They can make decisions in real time, adapt to unexpected situations, and perform complex tasks that would be difficult to automate. This is true, but it's also becoming less true every year as robotics and artificial intelligence advance rapidly. A comprehensive economic analysis published in 2025 by researchers at MIT compared the cost-effectiveness of human versus robotic lunar exploration across different mission scenarios. Their conclusion was stark. For purely scientific objectives, robotic missions were more cost-effective in every scenario examined. The only cases where human presence provided clear advantages were in construction and assembly of large structures, and even then, the advantage disappeared if you factored in the cost of keeping humans alive. So if it's not primarily about science, what's the real motivation? Resource extraction is the next justification. Mine the moon for valuable materials, extract helium-3 for future fusion reactors, process regolith for metals and building materials, produce propellant for refueling spacecraft headed to Mars or the outer solar system. The economic arguments here become very speculative very quickly. Yes, there's helium-3 on the moon, implanted in the regolith by the solar wind over billions of years. And yes, helium-3 is a potential fuel for fusion reactors, but we don't have working fusion power plants on Earth yet. We've been 30 years away from practical fusion power for the last 50 years. Building an entire lunar mining infrastructure to extract a resource for a technology that doesn't exist yet seems like putting the cart several miles ahead of the horse. What about mining metals or manufacturing materials for use in space? This is more plausible. If you're building large structures in orbit or assembling spacecraft for deep space missions, it's theoretically cheaper to bring materials from the moon than from Earth because of the moon's much lower gravity. But this only makes economic sense if you're building things in space on a large enough scale to justify the enormous upfront investment in lunar mining and processing infrastructure. We're talking about billions, possibly hundreds of billions of dollars in development and construction costs before you extract your first kilogram of useful material. Who's going to pay for that? Government space agencies have limited budgets and competing priorities. Private companies need to see a path to profitability, and the timeline from investment to return is measured in decades, not years. That's a tough sell to investors and shareholders. Some advocates point to space tourism as a revenue source, wealthy individuals paying millions for a trip to a lunar base. This could provide some income, but the market is limited. How many people can afford to pay, let's say conservatively, $10 to $20 million for a lunar vacation? And of those who can afford it, how many are willing to accept the risks and physical demands of the journey? Space Adventures, the company that arranged several tourist flights to the International Space Station in the 2000s, charged around 20 to 30 million per seat for trips that lasted about 10 days. A lunar trip would be more expensive, longer, and significantly more dangerous. The market probably exists, but it's not large enough to fund the infrastructure development on its own. Then there's the strategic and geopolitical rationale, which is probably closer to the real driver behind current lunar ambitions. Even if it's not always stated explicitly, the moon represents high ground in a geopolitical sense. Not for military purposes necessarily. though that's certainly part of some nations' thinking. But, as a demonstration of technological capability, economic strength and long-term vision, the nation or coalition that establishes a permanent presence on the moon first gains prestige, influence, and potentially economic advantages that compound over time. This was explicitly the motivation behind Apollo. The United States went to the moon to demonstrate technological superiority over the Soviet Union during the Cold War. The scientific returns were valuable, but they were secondary to the political objective. President Kennedy's famous speech didn't say, "We choose to go to the moon because of the fascinating questions about lunar geology." He said, "We choose to go to the moon because it's hard, because it will demonstrate what America can accomplish, because it serves to organize and measure our abilities." Today, we're seeing similar dynamics emerge. China has made remarkable progress in its lunar program with the Chang'e missions. They've landed on the far side of the moon, returned samples, and announced plans for a lunar research station in partnership with Russia. The United States has responded with the Artemis program, accelerating plans to return humans to the moon and establish a sustained presence. Europe, Japan, India, and other spacefaring nations are also developing lunar capabilities, often in partnership with the US or China. Private companies like SpaceX and Blue Origin are developing the heavy-lift rockets necessary to transport large payloads to the moon. Everyone is positioning themselves for what they see as the next phase of space exploration and exploitation. Nobody wants to be left behind. And this creates a dynamic where rational economic calculations about cost-effectiveness get overridden by strategic imperatives. But this emerging competition raises thorny questions about governance, law, and resource rights that the international community hasn't adequately addressed. The Outer Space Treaty, signed in 1967, establishes the basic framework for space law. It declares that outer space, including the moon and other celestial bodies, is not subject to national appropriation. No country can claim sovereignty over the moon. It's the common heritage of all humanity. The treaty also states that space shall be used for peaceful purposes and that nations bear responsibility for their activities in space, whether conducted by government agencies or private entities. Sounds good in principle, but the treaty was written during the Cold War when space activities were exclusively governmental and nobody was seriously planning commercial exploitation of extraterrestrial resources. The language is vague on crucial questions that matter now. Can a private company own the resources it extracts from the moon? Can they claim exclusive rights to a mining site? What happens if two entities want to use the same location? Who has jurisdiction if there's a dispute or if crimes are committed on a lunar base? The United States passed the Commercial Space Launch Competitiveness Act in 2015, which explicitly allows US citizens and companies to own resources extracted from celestial bodies. Luxembourg passed similar legislation. These laws try to provide legal clarity for companies investing in space resource extraction. But these are national laws, not international agreements. Russia, China, and several other countries have raised objections, arguing that these laws violate the spirit, if not the letter, of the Outer Space Treaty. They argue that allowing ownership of extracted resources is functionally equivalent to claiming sovereignty, which the treaty prohibits. There's no international court with clear jurisdiction to resolve these disputes. The mechanisms for enforcement are unclear, and as more nations and companies become active on the moon, the potential for conflict increases. Let me give you a concrete scenario that illustrates the problem. Imagine it's 2035. A US company has established a small mining operation at the lunar South Pole, extracting ice from a permanently shadowed crater. They've invested billions of dollars in the infrastructure. A few kilometers away, A Chinese scientific station is conducting research. Both facilities need power. The best location for solar panels is a small peak that receives nearly continuous sunlight, one of those peaks of eternal light we discussed earlier. Both the US company and the Chinese station want to place their solar arrays on that peak. Who has the right to use it? First come, first served. Is there enough room to share? What if one party was there first, but the other can demonstrate they filed plans or claims earlier? What if the solar panels interfere with each other, casting shadows or creating operational problems? Under current international law, there's no clear answer. The Outer Space Treaty says space activities should benefit all countries and that nations should conduct exploration with due regard for the interests of others. But what does due regard mean in practice? How do you balance competing claims when both parties have legitimate interests? Now scale this up. Imagine 10 different entities from 6 different countries, all operating in the same region because that's where the resources are. Some government, some private, all competing for access to ice, to the best landing sites, to solar power locations, to communication relay positions. Add in the fact that activities on the moon can have unintended consequences for neighbors. A mining operation kicks up dust that travels for kilometers in the low gravity and vacuum, potentially contaminating scientific instruments or coating solar panels. Rocket launches and landings create vibrations that could affect sensitive seismic experiments. Radio transmissions interfere with astronomical observations. On Earth, we have centuries of evolved property law, regulatory frameworks, and dispute resolution mechanisms to handle these issues. On the moon, we're making it up as we go, and the stakes are potentially enormous. The United Nations Committee on the Peaceful Uses of Outer Space has been working on these issues, but progress is slow because the interests of spacefaring nations diverge significantly. Countries that have invested heavily in space capabilities want frameworks that protect their investments and allow them to benefit from resources they extract. Countries without advanced space programs worry about being locked out of access to space resources and want frameworks that preserve the common heritage principle. Various proposals have been floated. International registries for lunar activities, keep out zones around operating sites, mandatory coordination before establishing new facilities, binding arbitration for disputes. But getting international agreement on binding rules is difficult when the major spacefaring powers have fundamentally different visions for how lunar resources should be governed. Meanwhile, activities proceed. Companies and nations make plans and investments based on their interpretation of existing law and their calculation of what they can get away with. This creates facts on the ground, or rather, on the moon, that shape future negotiations. There's a real risk that we're setting ourselves up for conflicts that could range from diplomatic disputes to, in worst-case scenarios, actual confrontations. And when you have multiple nations operating nuclear reactors and potentially dual-use technologies on the moon, the consequences of miscalculation or escalation could be severe. Some people dismiss these concerns, arguing that space is vast and there's room for everyone. But that's not actually true for the moon's most valuable locations. The areas with accessible ice, good solar power potential, and suitable terrain for construction are limited. The lunar South Pole region, where most activity is planned, is maybe a few hundred square kilometers where all the favorable conditions come together. Think of it like Antarctica, which is also governed by an international treaty that prohibits territorial claims. Multiple nations operate research stations there, generally cooperating, but also sometimes competing for the best locations. Disputes are resolved through diplomacy and the structures of the Antarctic Treaty System, but Antarctica has something the moon doesn't. It's on Earth. Personnel can be evacuated if necessary. Supplies can be delivered relatively quickly. There's international oversight and inspection regimes. Most importantly, the cost and difficulty of operations in Antarctica naturally limit how many facilities get established. The Moon has none of these natural limiting factors, or rather, the limiting factors are so extreme that only the most committed and well-funded actors will be there, and those actors will have invested so much that they cannot afford to walk away from disputes. This creates a situation where the stakes are high, the rules are unclear, and the ability to enforce agreements is limited. It's not a recipe for harmonious international cooperation. Now, having laid out all these challenges, the technical nightmares, the crushing costs, the unsolved medical problems, the legal ambiguities, the geopolitical tensions, let me address the question that's probably on your mind. Is lunar colonization actually going to happen? And if so, when? The honest answer is, yes, probably, but not on the timelines or the scale that advocates often suggest, and not necessarily in the form people imagine. Let's talk about realistic timelines based on current progress and the technical challenges we've discussed. The Artemis program, NASA's current plan for returning humans to the Moon, aims to land astronauts on the lunar surface by the late 2020s. This is already several years behind the original schedule, and further delays are likely given the complexity of the systems being developed. But let's assume humans return to the Moon by 2028 or 29. Those initial missions will be similar to Apollo. Short duration visits, a few days on the surface, focused on exploration and demonstrating capability. This is not colonization. This is planting flags and proving we can still do what we did 50+ years ago with updated technology. The next phase would involve extended duration missions. Crews staying for weeks or potentially months, using pre-positioned habitats and equipment. NASA has discussed establishing an Artemis base camp, a small facility to support these longer missions. Optimistically, this might happen in the early to mid-2030s if development proceeds well and funding remains consistent, both significant ifs. This would still not be colonization in any meaningful sense. It would be more analogous to Antarctic research stations, small numbers of personnel rotating through, entirely dependent on supplies from Earth, conducting research and demonstrating operational capabilities. For actual colonization, a permanent, self-sustaining presence that doesn't depend on constant resupply from Earth, we're talking about a significantly longer timeline. You need to develop and deploy all the infrastructure we've discussed. Reliable power generation, life support systems, radiation protection, construction capabilities, manufacturing and repair facilities, propellant production, medical capabilities, and some level of food production. We've talked about moon dust slicing through lungs, radiation destroying DNA, but here's something refreshing. Something you can actually do about understanding space tonight. Download Mars in 15 minutes. No expensive equipment. No waiting for space agencies. Just you, 15 minutes of reading, and the ability to recognize Mars in the sky for the rest of your life. The link in the description and pinned on the comments. While they figure out how to survive the Moon, you figure out how to navigate the night sky. Each of these systems needs to be developed, tested, deployed, and proven reliable. Many depend on each other, so you can't develop them all in parallel. You need power before you can run life support. You need life support before you can support crews for extended periods. You need extended crew presence before you can construct and operate manufacturing facilities. Engineers and project managers use a concept called technology readiness levels to assess how far along a technology is from initial concept to fully operational. Many of the critical systems needed for lunar colonization are currently at TRL 4 or 5, meaning they've been demonstrated in laboratory or relevant environments but aren't ready for operational deployment. Getting technologies from TRL-5 to TRL-9 fully operational in mission environments typically takes 10 to 15 years and hundreds of millions to billions of dollars, depending on complexity. And you need dozens of these technologies, all reaching operational readiness and working together reliably. The integration challenges are immense, based on historical patterns in space program development. And accounting for the technical challenges we've discussed, my assessment is that a truly permanent, minimally self-sustaining lunar presence is realistically 30 to 50 years away. That means we might see something that could genuinely be called a lunar colony, not just a research station, somewhere between 2055 and 2075. I know that sounds pessimistic compared to what you often hear from space agencies and commercial space companies, but it's grounded in the realities of technology development timelines, funding constraints, and the extraordinary difficulty of what's being attempted. Could it happen faster? Sure, if there's a massive increase in funding and international cooperation. If technological breakthroughs solve key problems more quickly than expected. If competition between nations or billionaire entrepreneurs accelerates development. Apollo went from Kennedy's speech to boots on the moon in 8 years because the United States committed enormous resources and political will to making it happen. But Apollo was a sprint, not a marathon. It was unsustainable, which is why we left after a few missions and didn't return for half a century. Building a permanent lunar colony is not a sprint. It's a multi-generational marathon that requires sustained commitment and investment over decades, which brings us to the final, most fundamental question. Should we do this? Is establishing a lunar colony worth the cost, the risk, the effort, and the opportunity cost of not spending those resources on other priorities? I'm going to give you an answer that might be unsatisfying, but it's honest. It depends on what we're trying to accomplish and what we value as a civilization. If the goal is purely scientific knowledge about the moon and the solar system, then no, massive investment in human lunar colonization probably isn't the most efficient approach. Robotic missions deliver more science per dollar with vastly lower risk. If the goal is economic return through resource extraction or space industrialization, then the business case is questionable at best with current technology and foreseeable markets. The upfront investment is staggering, the timeline to profitability is measured in decades, and there are significant technical and legal risks. If the goal is ensuring human survival by creating a backup civilization off Earth, then the moon is honestly not an ideal choice. It's too close to Earth. Any catastrophe that makes Earth uninhabitable might affect the moon as well. It lacks the resources for true self-sufficiency. Mars or free space habitats make more sense for this purpose, though they come with their own enormous challenges. But if we view lunar colonization as a stepping stone, a way to learn how to live and work off Earth, to develop the technologies and operational experience needed for further exploration, to inspire new generations of scientists and engineers, to expand human civilization beyond a single planet, because that's simply what humans do, then perhaps the cost and risk are justifiable. There's something deeply human about pushing boundaries, exploring new frontiers, and attempting things simply because they're hard. The Apollo program inspired millions, drove technological innovation, and demonstrated what humanity could accomplish when focused on a grand challenge. A successful program of lunar colonization could have similar effects, spurring advances in robotics, materials science, life support, energy systems, and countless other fields. The technologies developed for living on the moon will have applications on Earth. Better radiation protection, more efficient closed-loop life support, advanced manufacturing techniques, improved medical monitoring systems. These innovations could benefit humanity broadly, and there's an argument that having multiple spacefaring nations and companies working toward lunar presence creates a competitive dynamic that accelerates progress and reduces the risk that we stagnate as a civilization. But, and this is a significant but, these benefits need to be weighed against opportunity costs. Every dollar spent on lunar colonization is a dollar not spent on addressing climate change or curing diseases, or improving education or developing clean energy or any number of pressing challenges here on Earth where billions of people live. Reasonable people can disagree about where that balance lies. My personal view, for what it's worth, is that a measured, sustainable program of lunar exploration and gradual development of infrastructure makes sense. Not crash programs with unrealistic timelines that lead to cost overruns and disappointment. Not grandiose visions of moon cities with thousands of inhabitants that ignore the brutal realities of the environment. Instead, think of it as a long-term project that proceeds step by step, learning at each stage, building capability gradually, and maintaining perspective about what we're trying to accomplish and why. Small crews rotating through for gradually longer durations, incremental development of capabilities for resource utilization, international cooperation on core infrastructure while allowing competition in specific applications, research stations that genuinely advance our knowledge while proving out technologies that could enable further expansion. If, after decades of this measured approach, we've demonstrated that larger-scale lunar presence is technically feasible and economically or scientifically valuable, then we can consider expanding. If we find that the challenges are more intractable than anticipated, or that the benefits don't justify the costs, we can adjust our approach. This isn't as exciting as visions of lunar cities and thriving off-world civilization, but it's realistic, it's sustainable, and it respects both the extraordinary difficulty of what's being attempted and the competing priorities we face as a species. The moon has been there for 4.5 billion years. It'll be there for billions more. We don't need to colonize it in the next decade to consider ourselves successful. What we need is to approach this challenge with clear eyes, honest assessment of the difficulties, sustainable commitment, and genuine thoughtfulness about what we're trying to accomplish, because ultimately the question isn't whether we can establish a permanent human presence on the moon. With sufficient time, resources, and commitment, we probably can. The question is whether we should and what success actually looks like. That's a question that doesn't have a purely technical answer. It requires weighing values, considering opportunity costs, and thinking carefully about what kind of future we want to build and how we want to get there. The moon is an extraordinary destination. Establishing a human presence there would be a remarkable achievement. But it won't be easy, it won't be cheap, and it won't happen as quickly as the optimists suggest. Anyone telling you otherwise, Anion promising lunar colonies in 5 years, or claiming it'll be easy and profitable, or glossing over the technical challenges, is either uninformed, selling something, or both. The reality of lunar colonization is that it's one of the hardest things our species has ever attempted. It will require decades of sustained effort, countless technological innovations, international cooperation on an unprecedented scale, and acceptance of significant risks. Whether we choose to pursue it and how we go about it will say something profound about who we are as a civilization and what we value.